Hello friend, today we will just see the next topic of online series, and today's topic is exact differentiable equation. Before we start exact differentiable equation, we already saw what is the mean by differentiable equation, how to find its order, degree, which is already covered in previous lecture. Today we will just move towards the new topic, that is exact differentiable equation. So what does it mean by exact differentiable equation? We know the differentiable equation whose form, that is mdx plus ndy is equal to 0 is my differentiable equation. And this differentiable equation is said to be exact when there is a condition. mdx plus ndy is my differentiable equation, and we have to identify whether this my given differentiable equation is exact or not. If it is exact, then what is the actual meaning of your exactness, and how to just find the exact condition of the given differentiable equation. The differentiable equation mdx plus ndy is exist if there exists some function u which is in terms of x and y. It means u is a function of your x and y variable. When we differentiate this u with respect to your x and y, that is finding the total derivative of your function u, we get du. When the differentiable equation m dx plus n dy is exactly equal to the derivative of your u, then we say that the given differentiable equation is exact. There is a simple rule to identify whether the given function is exact or not. The sufficient condition of the exactness is if mdx plus ndy is equal to 0 is my differentiable equation, we have to differentiate your m with respect to y, n with respect to x, when the derivative of your m with respect to y and the derivative of your n with respect to x both are equal, then the given differentiable equation is exact. This dava m upon dava y is equal to dava n upon dava x is the necessary and sufficient condition to check whether the given differentiable equation is exact or not. If the partial derivative of your m with y and the partial derivative of your n with x, these derivatives are identical or same, then given differentiable equation is exact. This is the simple criteria to find the exact. If the differentiable equation is exact, then how to find the solution? Then there are two different rules to find the solution of the exact differentiable equation. The rule number one is that we have to find the solution of the given exact differentiable equation by any one of the rules. Rule number one is we have to integrate your m with respect to x, keeping y as a constant. If your m is a function of your xy variable, we have to integrate your m with respect to x variable only. At the same time, we have to keep y variable as a constant. And in the second integration, we have to just eliminate the variable y which is present in your n. It means the terms which containing x we have to remove from your n, and the remaining terms we have to take integration with respect to y. So the general formula to find the general solution of your exact is integration of your m with respect to x, keeping y as a constant, and the terms does not containing x in your n, integrate such a terms with respect to y, we get the first solution or the solution of your exact differentiable equation. In another way, we can find the solution of such a differentiable equation by reversing the process. Means we have to follow the rule number second. We have to just take the integration of your n with respect to y variable. At the same times, we have to keep x variable constant. In second integration, we have to just eliminate the terms which is present in your n, and that terms are nothing but variable y. The y which is present in those terms we have to remove from your m and choose the remaining terms, find its derivative with respect to x. With respect to x, this is the procedure, or this is the two rules to find the solution of your exact differentiable equation. So we will see how to just find the general solution of the exact differentiable equation by some examples. So we will move forward to find the solution of such a differentiable equation. The first we have to just know how to just what is the procedure to find the solution. The equation number the equation is given. We have to check whether the given equation is exact or not. The first the example is given. Solve dy by dx is equal to y plus 1 divided by y plus 2 is multiplied by e raised to y minus x. So we have to just find its solution. This example is not in a variable separable form, because the coefficient of your dx is converted into only function of x, as well as the coefficient of your dy is not converted into only the function y. So the given example is not a variable separable form. So we cannot find the solution by using variable separable form method. Then what we have to do? We have to just check whether the given differentiable equation is exact or not. For that, we have to just consider the given equation. This equation is given. We have to make the rearrangement of this differentiable equation. So what we have to do? We have to make the cross multiplication. We are just multiplying, cross multiplication. So this dy is get multiplied denominator of your right hand side, that is a y plus 2 into e raised to y minus x dy, and your y plus 1 is get multiplied by dx. This is the separation of the equation by making the cross multiplication. After that, we have to convert this differentiable equation in mdx plus ndy form. For that, we have to shift your left hand side to right hand side, or left hand terms to right hand. It depends on that we are making the separation. The separation is here. We are converting this. We are shifted this particular terms to right hand side. It becomes negative. And in the next step, we are making the rearrangement of your terms. The minus sign get multiplied to your term number second. So we are multiplying with minus sign in the bracket. The first y plus 2 becomes negative and your minus x becomes positive. So we get a differentiable equation in the form of dx plus ndy. When we compare this equation with your standard differentiable equation, mdx plus ndy, then the value of your m is equal to y plus 1. And your value of your n is equal to minus times y plus 2 e raised to yx. This is the value of your m and n. In such a differentiable equation, we got m and n. So we have to differentiate your m with respect to y and n with respect to x. When we differentiating this, and we have to check whether both the derivatives are equal or not. If they are equal, then your differentiable equation is exact. Otherwise, it is not exact. So differentiating your m with respect to y and differentiating your n with respect to x, we get the derivative of your m with respect to y is 1. Because m contains y plus 1. The derivative of your y with respect to y is 1. Derivative of your 1 is 0. So the derivative of your m with respect to y is becomes 1. In similar way, we have to find the derivative of your n with respect to x. When we differentiating with respect to x, at the time y becomes constant. Means your first term, it is a minus y plus 2 into e raised to y is my constant, and the derivative of your constant is 0. And plus x, whose derivative is 1. So after taking the derivative of your m and n with respect to y and x respectively, the dy m upon dy y, whose value is 1, and dy n upon dy x, whose value is also 1. When these two ratios or the two derivatives are equal, this is the necessary and the sufficient condition of your exactness. If both the derivatives are same, then the given differentiable equation is exact. So the derivative of your m with respect to y and the derivative of your n with respect to x, both are equal. So the given differentiable equation is exact. So we represent here the given differentiable equation is exact, and we can find its general solution by using any one of the rule. Rule number 1 or rule number 2 depends on us. So we can find the solution of such a differentiable equation by using rule number 1. The rule number 1 tells us we have to integrate your m with respect to x. At the same time, we have to keep y as a constant variable. In the second integration, we have to remove the terms which is containing x. Then we have to remove that particular terms. Then we have to just take the equations. The m is nothing but your y plus 1. We have to just put the value of your m as it is. This is the your m equation. Means m is equal to y plus 1, which is present here. Again, in your n, the terms which is containing x, we have to remove that. And n, what is there? N is nothing but your minus y plus 2 e raised to y plus x. Means plus x, in which x is present. So we have to remove this x. After removing this x, only minus y plus 2 e raised to y is present. So we have to put that value here. And we have to find the integration. The first, the y is constant. So y plus 1 also a constant. We are taking that constant outside your integration. So we can find the integration of your y plus 1 is with respect to x is x. The integration of your dx becomes x. Then here y plus 2 and e raised to y, there are two functions of y. We have to use the product rule of your integration. The first function remains as it is. We just keeping the first function as it is. Second function integration, the e raised to x whose integration is e raised to x. Then minus sign. First function derivative. The first term is your 1 plus y plus 2. The derivative of your y with respect to y is 1 and the derivative of your 2 is 0. Then 1 plus 0 and again second function, that is e raised to y, is integration 2 times. And we know that the exponential functions in the integration 1 times, 2 times or several times is itself. So we get 1 plus 0 into e raised to y. In the third step, what we have to do? The terms which is present in your second, we have to differentiate. That is a 1 plus 0 is a term. And the derivative of your 1 is 0. So we got 0 into e raised to y. This is the integration by using the Bernoulli's equation, Bernoulli's integration. So after making the rearrangement, we get a final solution of such a differentiable equation. That is a y plus x, y plus 1 into x. And this y plus 2 into e raised to y. And this e raised to y, this 2 and this minus 1 becomes plus 1. Means y plus 1 are common. When we just take the common y plus 1, we get the final solution, that is y plus 1 into x minus e raised to y is equal to c, and c is the constant of integration. In this way, we can find the solution of any exact differentiable equation. So we will just move for the next example, then you will just get all the idea will clear. Example number second is here. Solve y into e raised to xy minus tan x into dx plus x e raised to y minus sec y dy is equal to 0. So this is the differentiable equation is given and we have to find its solution. Solve indicates we have to find its solution. So for that, we have to check whether the given differentiable equation is exact or not. For that, we are representing the given differentiable equation. The equation in the form of m dx plus n dy form. So comparing this differentiable equation with m dx plus n dy, the value of your m is equal to y e raised to xy minus tan x. And value of your n is equal to x e raised to xy minus sec y. Differentiating these two equations, that is m and n, with respect to y and with respect to x respectively. So differentiation of your m with respect to y and differentiation of your n with respect to x, we get the following derivatives. So the y and e raised to xy, we have to use the product rule because we have to differentiate with respect to y. So first, the derivative of your y with respect to y becomes 1 and e raised to xy remains as it is, plus y remains as it is, and the derivative of your e raised to xy is e raised to xy. But the index of your exponential function is xy. Again, we have to differentiate xy with respect to y. In a similar manner, the n containing x e raised to xy minus sec y. And we have to differentiate this particular equation with respect to x. So derivative of your x with respect to x is 1. E raised to xy remains constant. Plus the second function, we have to take its derivative. So derivative of your e raised to xy is e raised to xy. And the index of your exponential function is xy. So we have to differentiate that xy with respect to x. So after taking the derivative of your xy with respect to y and x, the derivative of your m with respect to y is e raised to xy, xy e raised to xy. And the derivative of your n with respect to x is e raised to xy plus x e raised to n. When we observe these two derivatives, The m is differentiated with y, n is differentiated with x. Both the derivatives are same. So we say that by the necessary and the sufficient condition, this differentiable equation is exact. So we say that the given differentiable equation is exact, so we can find its general solution by using either rule number 1 or rule number 2. We will use rule number 1 here. The rule number 1 indicates the derivative of integration of your m with respect to x, keeping y constant, and the integration of your n that does not containing x with respect to y. So the equation of your m, we have to write the equation of your m as it is, an integration sign. So we get integration with respect to x, keeping y as a constant, y times e raised to x, y minus tan x is your equation m. And in n, the n is equation which is present here, so see here. In this equation, the terms which containing x, we have to remove such a terms. The term number first containing x into e raised to xy, so we have to remove these whole terms. After removing the whole terms, we get only minus sec y. So we have to find the integration of your sec y with respect to y only. After taking the integration with respect to x, the y is constant. So y remains constant. Integration of your e raised to xy is e raised to xy divided by y. Before taking integration, we make the simplified form of your tan x. The tan x is nothing but your sin x upon cos x. The value of your tan x is nothing but your sin x upon cos x. We are representing tan x into sin x upon cos x. So taking the integration in the next step, we know that the integration of your e raised to x is e raised to x itself. But this x is get multiplied by y. So the y becomes divided after taking the integration. And integration of your sin x upon cos x is nothing but your log of sec x, or simply plus log of cos x, depends on your that conversion. There is no need to express these particular terms also. We can take the integration directly. That is integration of your e raised to xy is e raised to xy upon y. And integration of your log x, tan x is equal to log of sec x. And integration of your sec x is nothing but your sec x plus tan y. Here x is not present here, variable y is here. So we can take the integration of your sec y is log of sec y plus tan y. And after making the cancellation of this y, we get a final solution. And the final solution is e raised to xy minus log sec x minus log sec x sec y plus tan y is equal to c, which is the solution of my given differential.